Hello everyone, Kotongwane, the native god here. Right, let us take a look at this problem on reduction gearboxes and how you would approach such problems. Right, now if you have to, you can pause the video so you can read the information that you've been given, or so you can read the question. Right, but I've already taken the liberty of writing down the information that you've been given. Right, so as per the statement, we've been given the number of teeth of A, which is 27 number of teeth, and we're also given the moment of inertia of gear A, which is 0.46. The number of teeth of B is 43. Its moment of inertia is 0.84. The number of teeth of C is 30, and its moment of inertia is 0.65. The number of teeth of D is 40, and its moment of inertia is 0.46. And then if you look at our diagram here, right, we have this here, right, a flywheel which has been labeled as E, right, so it's on its mount on the input shaft. Right, so here you have a flywheel E which has a mass of 100 kilograms, right, and has a radius of gyration of 0.2 meters. Right, now let us look at questions. Right, but before we look at questions, as you can see on this figure, I've already labeled which gears we are taking as in and which ones we are taking as out. So since seeing that this is the input shaft, it means this is in, that's out. Right, you have the intermediate shaft, that's in, and that gear is out. And of course that gear is fitted with the output shaft. Right, now questions. Calculate the following. 7.1, the moment of inertia of the flywheel. All right, so we have all the necessary information to get the moment of inertia for the flywheel. Right, so that's 7.1. Right, seeing that the flywheel has been labeled as E, we're going to call this IE. Okay, maybe not that E, but capital letter E. Right, to differentiate between the what is the equivalent moment of inertia, right, and the moment of inertia of the flywheel. Right, so this is equal to, as we know, moment of inertia is mass times radius of gyration squared. Right, the mass of the flywheel is 100 kilograms. Radius of gyration, its radius of gyration is 0.2, so that's 0.2 all squared. Right, so this is the radius of gyration of the flywheel. Right, if you punch this in your calculators, we are going to get 4 kilogram meters squared. Right, now let's look at 7.2. Calculate the equivalent moment of inertia of the total system referring to the input shaft. Right, so essentially they want us to calculate IE1 here. All right, they want us to calculate the equivalent moment of inertia referring to the input shaft. Right, so if you look here, the input shaft is labeled as 1, the intermediate shaft I've labeled as 2, and then the output shaft I've labeled as 3. So if they want us to calculate the equivalent moment of inertia referring to the input shaft, there's your input shaft, meaning they want IE1. Right, equivalent moment of inertia for the input shaft. Right, now that, before we get to that, in fact, right, before we get to that, so this is 7.2. all right, now okay, let us write down the formula to calculate the equivalent moment of inertia referred to the input shaft. All right, now to calculate IE1, right, what you do is, or the formula would be I1 plus I2 times. Now normally here we would have the velocity ratio or gear ratio, and it would be in terms of N2 divided by N1. All right, so remember here if you're expressing the velocity ratio in terms of the rotational frequency, right, when calculating IE1, right, in terms of the, what is this, in terms of the velocity ratio or gear ratio, right, the denominator, right, is always going to be the, what is this, is always going to be based on what it is that we are calculating. So if you're calculating the, what is this, the equivalent moment of inertia referred to the input shaft, right? So because it's for the input shaft, then the denominator, right, will be the rotational frequency of the input shaft, so N1, right, plus, so by that I mean when having to add, right, I3, right, then multiplying this by the velocity ratio again, this would be N3, right, so the numerator will be based on this one here, right, and then the denominator, remember, just like I said, the denominator depends on what it is that you're calculating. So because you're calculating the equivalent moment of inertia for 1, right, the numerator will be 1 as well, right, so that's squared and that's squared, right. This is how we generally calculate the equivalent moment of inertia, right, for the input shaft, right. But now, if you look at our information here, we haven't been given the rotational frequencies of the shafts, right. What we've been given instead is the number of teeth of the gears, right. Now using number of teeth, right, using number of teeth, this would then be equal to I1 plus I2 times, now in terms of number of teeth, right, in terms of number of teeth, we are looking at the gear ratio between the input and the intermediate shaft, right, so between the input and intermediate shaft. So we look at the gears that are bringing these two shafts together, right, and those gears are A and B, right. Now if we look at, right, we have N2 over N1, right. Now to express this in terms of number of teeth, right, remember that the number of teeth will be essentially the inverse of what we have in terms of the rotational frequency, right. So for number of teeth, essentially what I mean by that is you would then have, you would have T1 over, right, T1 over T2, right, type thing, right. But because we're not necessarily looking at 1 and 2, right, we're looking at gears A and B, right. So we then look at, if you look at N1, that's the input, right, so essentially that is the output, right. So meaning in terms of number of teeth, this would have to be in over T out, right. Now if you look at the gears that are bringing these two shafts together, right, the one that is in is gear A, right, and the one that is out is gear B, meaning this would be TA divided by TB, right. So expressing, right, seeing that we do not have the rotational frequencies, right, to express the gear ratio in terms of number of teeth, we would then have to use this here for this one, right. So we would have TA divided by TB all squared plus I3 times, so we applied the very same thing here, right. If you look at how this gear ratio is expressed, it is in terms of N3 over N1, right, and N3, right, from the diagram we know N3 is the output shaft, right. So essentially what we have is N out over, and then N1 is the input shaft, so that's N in, right. And as we know how we express the gear ratio in terms of number of teeth, right, how we express it in terms of number of teeth, right, is opposite to how we express the gear ratio in terms of the rotational frequency, right? So seeing that it's n out that is at seeing that it's n out that is the numerator, it means in terms of number of teeth, right, you will have the product of t in here, right? So the product of t in, that would be ta times tc. So you would have ta times tc divided by the product of t out. T out is tb times td, right? Yes. Right, so seeing that we do not have the rotational frequency, we then express the velocity ratio in terms of number of teeth, right? So here you would have ta times t c divided by tb times td all squared, right? Now one thing is clear here, we have the number of teeth, but we don't necessarily have the moment of inertias, right? Now these moment of inertias, I1, I2, I3, right, that is essentially, we look at the inertia of all rotating bodies that are on the shaft, right? So for instance, I1, right, if you look at the input shaft, right, seeing that that is the one that we've labeled as 1, right? So I1, we would look at the inertia of any and all rotating bodies that are on the input shaft. Similarly with I2, right, we would add the moment of inertias of all the rotating bodies that are on the shaft. Similarly with 3, we will do the same, right? So if you look at 1, right, looking at what rotating bodies do we have on the shaft, it would be the flywheel and gear A, right? For I2, it would be gear B and gear C, and then for I3, it would only be gear D, right? Now, if the moment of inertia, right, of the shafts themselves has been given as well, then you would add that as well, right? But in this case, we haven't been given the we haven't been given the moment of inertia of any of these shafts, right? So meaning that it's likely negligible, right? That is why we haven't been given, right? So in calculating I1, or in calculating the equivalent moment of inertia, we need I1, I2, and I3, right? So let's first calculate those. All right, so let us first calculate those. So we have okay, so let us say calculating I1, right? So I1 would be equal to the moment of inertia of the flywheel plus the moment of inertia of gear A, right? So that would be 4 plus, so there will be 4, so IA is 4, and then IA is 0.46, so this will be 0.46, right? So this is equal to 4.46, right, kilogram meter squared, right? Then you calculate I2. The rotating bodies on the intermediate shaft is gear B and C, so this would be IB plus IC, right, which is equal to the 0.84 plus so P is 0.84, C is 0.65, 0.65, right? Now if you add that in your calculators, you would get 1.49 kilogram meter squared, right? And then I3, right, essentially is equal to ID, right? So the moment of inertia of gear D, which is equal to 0.46 kilogram meter squared, right? So we have I1, I2, as well as I3. We have all the number of teeth, so now we can get the what is the equivalent moment of inertia, right? So in calculating that, we then say IE1 is equal to I1, which is 0.46, 4,46. So this is 4,46 plus I2, right? I2 is the 1,49, so 1,49, right, into TA over TB, right? TA is 27 divided by TB, which is 43, right, squared, plus I3, which is 0.76, 0.76, all right, times TA times TC, all right, TA is 27, TC is 30, divided by TB, which is 43, times TD, which is 40, all squared. Right, now if you punch this in your calculators, we are going to get 5,216 kilogram meter squared, right? And that is how you would calculate the equivalent moment of inertia, right, referred to the input shaft, right? Right, then let's look at 7.3 now. 7.3, calculate the speed of the output shaft, right, at D in revs per minute after 30 seconds if a constant torque of 10 Newton meters is applied to the input shaft and acceleration is from rest, right, and the acceleration is from rest, right? So we need to calculate the output torque, right? We need to calculate the output torque. Now there's two approaches you can take here, right? There's two approaches you can take. One of those approaches is likely the most convenient one because we've already calculated the equivalent moment of inertia referred to the input shaft, right? So one of the approaches would be to calculate the acceleration of the angular acceleration of the input shaft, seeing that we've been given the torque and we've already calculated the equivalent moment of inertia referred to the input shaft, right? Once you have that, we then would have to use the gear ratio to calculate the angular acceleration, right, of the output shaft, right? Once you have that, we would then have to calculate what is it that we're looking for? We are looking for N, right? So we're looking for the rotational frequency of the of the input, of the output shaft, right? Of the output shaft, right? So you would calculate the angular acceleration, right, of the input shaft, use the gear ratio to calculate the angular acceleration of the output shaft, right? And then use then use equations of motion to calculate the rotational frequency of the output shaft, right? So that's the one approach. A different approach, or the second approach, or another approach you could try would be calculating the equivalent moment of inertia referred to the output shaft, right? Use the gear ratio to get the output torque, right? And then use, right, remember torque is equal to I times alpha, right? So once you've calculated the equivalent moment of inertia, right, referred to the output shaft, and you've calculated the torque, then you can calculate this here, right, which would be the angular acceleration of the output shaft. That once you have that, you can then use equations of motion, right, to calculate the rotational frequency of the output shaft, right? So that's another approach you can take, right? But between the two approaches, one is convenient, seeing that we've already calculated the equivalent moment of inertia referred to the input shaft, right? So this is 7.3, right? We already have the torque, right? The input torque is equal to the equivalent moment of inertia referred to the input shaft times the angular acceleration of the input shaft, right? So from this we can get the angular acceleration, right? Angular acceleration would then be equal to the input torque divided by IE1. So this is equal to, the torque has been given, it is 10 Newton meters, so divided by IE1, which is 5,216. So 5,216. All right, so now if you punch that in your calculators, we are going to get 1,917 radians per second squared, right? Right. Now that we have the angular acceleration for the input shaft, we can now use the gear ratio, right, to calculate the system's gear ratio, to calculate the the angular acceleration of the output shaft. Right, so remember that the gear ratio can be expressed in a number of ways, one of which is in terms of acceleration. Right, in terms of acceleration, the gear ratio is in over out. So this would be the angular acceleration of the input shaft divided by the angular acceleration of the output shaft, right? And then in terms of number of teeth, the gear ratio, how we express the gear ratio in terms of number of teeth, would be the product of T out divided by the product of Tn. All right, so T out here is Tb times Td divided by the product of T in, which is TA times TC, right? Now we have all the number of teeth, and now we've calculated this one here, so we can solve for this, right? Making the angular acceleration of the output shaft the subject, right? Essentially, what you would do is you just swap you swap the terms around, right? So meaning you take this, put it upstairs, take this, put it downstairs. You do the same thing this side, right? And then mathematically that would work out as, this would be TA times TC divided by TB times TD, right? And then of course this would be the numerator, right? This would be the numerator here, so you would say divided by that, right? But seeing that we are looking for the angular acceleration of the output shaft, right, then all you do is multiply by this term both sides. So here you would have times that, and of course that would be erased, right? So solving for this, we can now substitute. So substituting, TA is 27, TC is 30, right? Angular acceleration we've just calculated and got 1,917, right? All of this divided by, so TB, which is 43, right, times TD, which is 40, right? Now if you punch this in your calculators, we are going to get 0,903 radians per second squared, right? So now we have the angular acceleration for the output shaft, right? So now, seeing that based on what we've been given here, right, we have the angular acceleration, we also have time, right? We also essentially have the initial angular velocity, seeing that this moved from rest, right? So using one of the equations of motion that is convenient for us to use based on what we've been given. So that would be, we are looking for that, right, is equal to the initial, right, plus, what is this, angular acceleration of the output shaft, right, times time, right. This one is the most convenient, seeing that we have everything except what it is that we're looking for, right. So then this will be equal to this move from rest, so that's 0, plus this we calculated and got 0 0.903. The time is 30 seconds. Right, then if you punch this in your calculators, we are getting 27.09 radians, right, radians per second, right. Now they did say that we need to calculate the rotational frequency, right, and it must be in revs per minute. So from this we can now calculate the rotational frequency of the output shaft, right. We know the relationship between angular velocity and rotational frequency, right, is that omega, right. So this omega 3 would be equal to 2 pi n3, right. Right, now this has to be in revs per minute, so we divide this by 60, right. Now all you do is make n3 the subject of the formula. Making n3 the subject, this would be, right, 60 times omega 3 divided by 2 pi, right, divided by 2 pi, yes. Then now all you do is substitute. This would be 60 into, what is this, 27, yes, 27,09 divided by 2 pi, right. And then when you punch this in your calculators, we are getting 258,69 revs per minute, right. And that is how you would attempt such a question, right. Now, like I said, this is not the only approach that you can take, right, and I already explained the other approach that you could have taken, right. I used this approach because it was just a matter of convenience, right. Right, and that is how you would attempt such a problem, right. So I hope that you've learned something here, right. And then if you have any questions, we can talk about them in the comment section, right. Please like the video. If you found this content helpful, like the video. Also share with your fellow students, right. Cheers.